All right, we're going to go ahead and talk about winds and water. So, winds are caused by air movement. We all know that, right? Things move from one area to another. But wind is actually moved by the movement of air from areas of high pressure or cold air to areas of low pressure or warmer air. The larger the difference in temperature, the faster the wind moves. So if you have an area that has very high pressure, very cold air, and very low pressure, very warm air, you're going to get very quickly moving wind. Local winds are generally short distances, and they can blow in any direction. They can blow north, south, east, west, southeast, southwest, so on and so forth. And they move over small areas, so usually down a beach or down a canyon. And they are caused by different geographic features that produce temperature differences. So where there's a lake and where there's land, you may get more wind because of the unequal heating of these surfaces. So sea breezes. So over the ocean, right? We all know the ocean or a lake or something. It takes a lot more energy from the sun to heat a large body of water than it does to heat, let's say, a sandy beach. You would know that if you ever walked into the ocean or even a lake, okay, in the middle of a very hot day, and the sand that you're walking across is really, really hot, and the water is really, really cold. They're experiencing the same amount of heat absorption, but water can absorb way more heat than the land can or than the sand can. So you get an uneven heating. And because of that, the air above the ocean is colder, because it's not being heated as well, is colder or has higher pressure than the air over the land, which has been heated really well all day long. And so you have low pressure. And this is uneven heating, and because of that, the air moves from the ocean to the land, creating a sea breeze. So the air is going to move from the area of high pressure to the area of low pressure, and that means from the ocean or the body of water to the beach or the land, creating a sea breeze. So here's the diagram. So cold sea, meaning colder air, it's going to move towards the lower pressure or warm air over the land, and that's going to rise because warm air rises. It's going to create clouds, it's going to cool down, it's going to rain, so on and so forth. Land breezes. So low pressure occurs over the ocean during the night. So during the night, the water also maintains a lot more of its heat from the day, so it doesn't cool down or lose its heat very quickly. And so you get an area of low pressure over the ocean. And then the land, or the sand, or the beach, or the streets, or whatever, lose their heat very quickly at night, and so you get an area of high pressure or cold temperatures over the land due to the uneven heating. This causes winds to move from the land to the ocean, creating a land breeze. So on any given day, you'll see both of these local winds that occur, especially when you are right next to a body of water and a piece of land. So the other type of winds is the global winds, and these move over a long distance and are created by unequal heating over large areas. So air pressure. This is the difference in, this is really the cause. So air pressure is the cause of the uneven heating of the earth. So uneven heating produces pressure belts, and we're going to talk about what those are in a second. And they occur every 30 degrees in latitude. So here's our little diagram, and you'll see here's our equator, okay? And we have every 30 degrees, we are going to get a different wind belt, okay, or pressure belt. We're going to get a different pressure belt every 30 degrees. And you see they're called Hadley cells. And this tells you where the wind is moving. So essentially here you'll see the wind is rising at the equator where it's getting the most energy, cooling up top and circulating over here. And here you're going to see that the wind is going to rise over here and set over here. So you're going to get a different pressure belt at each 30 degrees. As warm air rises in the equator, it moves towards the poles and then it cools. As it cools, some of the air sinks around 30 degrees north and south of the equator. At the poles, cold air sinks and moves towards the equator. So we know that cold air sinks, so it's going to be below the warm air, and it's going to move the only way it can, which is towards the equator. Around 60 degrees north and south, the air begins to heat up and rise. And that's where we get our Coriolis effect. Okay, the Coriolis effect, I'm actually going to show you a quick video because this is going to be able to explain it. It explains it really well, much better than I can. So here you go.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Okay, so continuing on, I hope that made sense. The Coriolis effect is why we see spinning storms. Now we're going to continue our global winds. So a combination of the pressure belts, so these things we saw here where different areas cause different winds to rise and sink at different locations, as well as the Coriolis effect in the movie you just watched, which makes the winds in the northern hemisphere curve to the right and winds in the southern hemisphere curve to the left. The global winds are caused by these two things, the pressure belts and the Coriolis effect. And the global winds are the polar easterlies, the prevailing westerlies, and the trade winds. So this is a map of what they look like. The trade winds are closest to the equator, westerlies between 30 and 60 degrees, and the polar easterlies at the very top and the very bottom of the Earth. So the polar easterlies, wind belts that extend from the poles to 60 degrees latitude, both north and south. Cold winds that blow from the east to west near the north and south poles creates cold temperatures. So notice that they go from the east to the west, from the east to the west, in both the areas from 60 degrees, both north and south, to the poles. And they bring cold temperatures down, south. The prevailing westerlies, or the wind belts found between 30 and 60 degrees, both north and south, they flow towards the poles and from west to east, carrying moist air over the United States. So they go from west to east, and they carry wind from warmer air and moisture. Notice how it's mostly in the ocean, okay, from the south towards the north, so over the United States. And then we have our trade winds. These are steady winds that flow from east to west between 30 degrees latitude and 30 degrees south latitude. These are called the trade winds because this is what was used by early sailors. And they happen between or around the equator. And remember that along the equator, things above the equator are moving towards it. Okay, exactly like that. They are going to curve to the right or to the left. So that makes sense. Okay, jet stream. The jet streams are narrow belts of high wind speeds that blow in the upper troposphere. So this is basically the thing that's carrying the weather from one place to another. And it exists all the way from the upper troposphere along the tropopause into the lower stratosphere. And it separates warm air from cold air. So you'll notice the jet stream is right here. We've got cold air masses up here and warm air masses down here. Relative humidity. This is something you hear about a lot. This is the amount of water vapor in the air compared to the amount of water vapor the air could hold at a given temperature. So basically, when the air is completely saturated, you have 100% humidity because the air is completely maxed out and can no longer hold any more air. Whereas when you have very low humidity, the air could hold a lot more air, but it's not. A dew point, this is something we reach every day or most days. It's basically why you wake up in the morning and you can put your feet in the grass and the grass is wet. It's not because your sprinkler went on last night. It's because the temperature at which the air was fully saturated with the water vapor has been reached, which means the air begins to release that water vapor, not as rain, but just as dew on plants. Clouds. Okay, cloud classification. Clouds are grouped into three main groups. We know that clouds are made out of water vapor, I hope, that's condensed, or water droplets. Clouds can be cirrus, stratus, or cumulus. And the clouds are further classified by their altitude or location. Clouds form when water vapor in the air condenses to form liquid water or ice crystals. And scientists classify clouds into three main types, which I just told you, by their altitude. So cirrus clouds. Move down here. Okay, cirrus clouds are thin and feathery. Okay, they are generally occur in fair weather and point in the direction of the air movement. They are also very high, meaning when you're looking at the level that the clouds fall, they are technically very, very high in their altitude. We have stratus clouds. These are the layered clouds or low clouds. Stratus clouds stretch across the sky in low, large, flat layers, and they resemble fog, but they do not reach the ground. So if you look over here, okay, those are the ones that sit right on top of the mountains sometimes. Those would be your stratus clouds. And then you have your cumulus clouds. These are your puffy clouds. Okay, and they range from low to high level clouds, and these are the clouds that can produce heavy thunderstorms in the summer, and those cumulus clouds specifically are called cumulonimbus clouds, and they can extend for hundreds of meters upwards. So this is a little diagram that shows all of them. So we have a lot of stratus clouds down as low clouds. We've got cumulus clouds that are very middle, and they also go all the way up to the high ones. Okay, we have our cirrus clouds, which are mostly high clouds. Okay, so you can kind of see where they are, and this is altitude above ground level. So you can kind of see where they're located. All right, and that is our winds and water lecture. I hope you understood. Please write down any questions you have.